In this set of notes, we are tasked with finding the derivative function of e to the x and then any exponential function. First, you can see here that this initial task has already been completed, which was to find the value of this limit numerically. Of course, finding a limit numerically does not constitute proof that that's the exact solution, but we will trust that this limit is in fact 1. And you can see here are a couple of tables from Desmos showing that as you get closer to 0 from the left and from the right, the y values are getting closer and closer and closer to 1. So we're going to assume that that limit is 1. And we're going to use this to find the derivative function of e to the x. Right? So let's use the limit definition because we don't have the derivative function yet. That's why we have to go back to basic principles to find out what this derivative function is. So we've got f prime of x is equal to the limit as h approaches 0 of f of x plus h would be e to the x plus h, minus f of x would be minus e to the x, all over h. Now we want to rewrite this until this limit pops up in here somewhere. Well, first, e to the x plus h can be rewritten as e to the x times e to the h. That's a basic consequence of the exponent laws. So this is equal to the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. And now you can see we can factor out an e to the x out of the top here. This would give us the limit as h approaches 0 of e to the x times the quantity e to the h minus 1 all over h. And now you notice we've created this expression e to the h minus 1 over h in here. Since the limit is being taken with respect to h, that's not going to have an effect on this e to the x, so we can pull that out front of this limit. So this is equal to e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And as we saw, this limit right here is precisely 1. So this is simply e to the x. Hence, the derivative with respect to x of e to the x is the function e to the x itself. This is very interesting, and it's something that is worth knowing off the top of your head. Now, what about the derivatives of every other exponential function? So base other than e. So in general, again, our functions, our exponential functions are the form y equals a to the x, where a is greater than 0 and a is not equal to 1. We want to know, are their derivatives also themselves? Derivative of e to the x is e to the x. Is the derivative of a to the x also itself a to the x? That's what we're tasked with finding out here. First, what we're going to do is we're going to write x as a function of y, where y is equal to a to the x. So in order to isolate x here, we could take the natural log of both sides, for example, which would give us the natural log of y is equal to the natural log of a to the x. Now, the natural logarithm function is base e, not base a, so this is not simply just x. However, we can use the logarithm laws, specifically this one right here, that when you have a power, that can be brought down front. So this is the same thing as natural log of y is equal to x times the natural log of a. Now, ultimately, if we want to get x by itself, we can divide both sides by the natural log of a, and we get x is equal to the natural log of y divided by the natural log of a. Now, we're going to implicitly differentiate this new equation with respect to x. So we're going to take the derivative of both sides of this equation with respect to x. So we got d dx of x is equal to d dx of the natural log of y divided by the natural log of a. Well, first, the derivative with respect to x of x is just 1. Over here, this 1 over ln of a factor is not being affected by the differentiation. That's like a constant to the derivative. So we can pull the 1 over ln of a out front, and we get 1 over ln of a times the derivative with respect to x of the natural log of y. And here, in order to find this derivative, this is the implicit differentiation part. So again, we're assuming y is a function of x, and in fact, it actually was. And so we want to find the derivative of the natural log of y. Hence, you've got a function of x inside of another function of x. This means we need to use the chain rule. So we've got 1 equals 1 over the natural log of a times, now this derivative. We need the derivative of the outside function. The derivative of the natural log function with respect to x is 1 over x, but we don't want to evaluate it at x. Instead, we want to evaluate it at the inside function y. So instead of 1 over x, we've got 1 over y. And we still need to multiply by the derivative of the inside function. Well, y is a function of x, so the derivative of the inside function is exactly what we call dy dx. We can now isolate dy dx. We get dy dx is equal to y times the natural log of a. Since y was actually a function of x, we can plug a of x in for y in this derivative formula, which would give us dy dx is equal to a to the x times the natural log of a. So our derivative formula, when you have the derivative of a to the x, is precisely a to the x times an additional factor of ln of a. So the derivative of a to the x in general is not just a to the x. It's a to the x times the natural log of a. However, did our computations on the previous screen, do they still fit this particular formula? In other words, when a equals e, will this formula still yield the derivative of e to the x with respect to x is just e to the x? Well, let's go ahead and plug it in. So we've got d dx of e to the x is equal to e to the x times the natural log of e. So that was plugged directly into this formula here. But we know the natural log of e itself is 1, so this really is just e to the x. So the derivative of e to the x is equal to e to the x. It's a consequence of this overall general formula for finding derivatives with respect to x of exponential functions.